Recall in the previous video, we found that linear momentum is conserved in a system where there are no external forces acting on the system, or the external forces are negligible. As a result, we can always apply the conservation of linear momentum equations to a collision, which are these equations in 2 dimensions. On the other hand, kinetic energy may or may not be conserved depending on the type of collision. For example, consider bouncing a ball off of the floor. If the ball is very bouncy, then it will lose very little energy when it impacts the floor. So its final velocity just after it leaves the floor will be nearly the same as its initial velocity just before it hits the floor. So we can say, at least approximately, that V final equals V initial. As a result, kinetic energy is approximately conserved, and we can say that kinetic energy final equals kinetic energy initial. On the other hand, what if the ball is not very bouncy, like say a basketball that hasn't been pumped up very well? Then the final velocity will be less than the initial velocity, and as a result, the final kinetic energy will be less than the initial kinetic energy. So in this case, some of the kinetic energy is dissipated as heat and sound, and so kinetic energy is not conserved. Based on these 2 scenarios, we classify collisions as either elastic or inelastic, where in an elastic collision, kinetic energy is conserved, or at least is approximately conserved, and in an inelastic collision, kinetic energy is not conserved. There is also a special case of an inelastic collision where the colliding objects stick together. For instance, if you drop a beanbag onto the floor, it doesn't bounce at all. Then all of the kinetic energy has been lost, so clearly kinetic energy is not conserved. In fact, when objects stick together like this, the maximum amount of kinetic energy is actually lost. We refer to these collisions when objects stick together as perfectly inelastic collisions. The fact that the objects stick together means their final velocities are the same, and we can make use of that fact when we solve problems. We'll discuss each of these types of collisions one at a time and go over some basic applications. Let's start with perfectly inelastic collisions because they tend to be the easiest to solve. To sum up what we said about perfectly inelastic collisions, linear momentum is conserved, as it is for all of our collision problems, and this means that the conservation of linear momentum equations apply. On the other hand, kinetic energy is not conserved, and finally they stick together. So V final for object 1 equals V final for object 2. Here's an example of a perfectly inelastic collision. William Tell shoots an arrow into an apple that is sitting on top of a fence post. The arrow sticks into the apple and it flies off the fence post. The arrow has a mass of 30 grams and the apple has a mass of 90 grams. Just before impact, the arrow is traveling horizontally at 40 meters per second. What is the speed of the apple with the arrow stuck in it when it flies off the fence post? The first step from the procedure in the last video is to draw a diagram, where I've called the arrow object 1 and the apple object 2. The next thing we need to do is to identify the type of collision. The title of the example already tells us that it is a perfectly inelastic collision, but we should be able to recognize that given the fact that the objects stick together. Then we can write down the conservation of momentum equation. Because all of the motion is in the x direction, we just need to use the conservation of momentum in that direction. Next, we can recognize that the initial velocity for object 2, the apple, is 0, and we can recognize that the final velocity for object 1 equals the final velocity for object 2, so we can just make them the same final velocity variable. So now the equation simplifies to this, and we can solve it for V final, plug in values, and we find that the final speed of the apple with the arrow stuck in it is 10 meters per second. This is a basic one-dimensional example to demonstrate the procedure to follow. There are some additional worked out examples posted, including a 2-dimensional example that you should review. Now let's discuss elastic collisions. As previously indicated, linear momentum is conserved, again, as it is for all collisions. So the conservation of linear momentum equations apply, and this time kinetic energy is conserved, so the total initial kinetic energy of the system, 1/2 mv squared for object 1 plus 1/2 mv squared for object 2 initially equals 1/2 mv squared for object 1 plus 1/2 mv squared for object 2 finally. In a two-dimensional problem, using these three equations and combining them algebraically can be a bit messy. However, when a problem is one-dimensional, there is a simplification that we can make. Before I provide the simplification, let me first explain what is meant by a one-dimensional problem and a two-dimensional problem. In a one-dimensional problem, the collision is head-on, and that causes all of the motion to be in a straight line. As an example, here is a video clip from the sport of curling. In the clip, you'll see one stone, as they're called, hit another stone, and then all of the motion is in a straight line. And then here is another curling match where the collision is not head-on, and that causes the stones to move off at angles, and thus the motion is in two dimensions. So now back to our equations. As I said, if the collision is in two dimensions, all three of these equations must be used as written. But if the collision is head-on, and therefore one-dimensional, the equations can be simplified. The first simplification is obvious. Because the motion is one-dimensional, then only one of the conservation of momentum equations is required, say the x direction. In addition to that, the conservation of kinetic energy equation can be greatly modified by algebraically combining it with the conservation of momentum equation. The result is that we still have the conservation of linear momentum equation as written, but the conservation of kinetic energy equation becomes V1 minus V2 initial equals V2 minus V1 final. So for a one-dimensional or head-on elastic collision, only these two equations are required. And so the math is much easier. The algebraic derivation of this modified equation can be found in textbooks, and I won't go through it here. However, this result can be explained with relative velocity. Consider two objects heading towards each other with the velocities shown here. From object 2's perspective, object 1 appears to be moving toward object 2 at 6 meters per second. This is obtained mathematically by V1 minus V2. Then, if the objects collide with a head-on collision, from object 2's perspective, object 1 will then appear to be moving back the other way, something like this. The actual velocities depend on the relative masses of the two objects, but because kinetic energy is conserved, the speed of object 1 from object 2's perspective must still be 6 meters per second. And mathematically, this is obtained by V2 minus V1. And so you can see from this analysis that V1 minus V2 initial equals V2 minus V1 final. And this is the simplified equation that I had previously written down. I'll work through a one-dimensional elastic example to demonstrate how to use these equations. Two toy carts are on a track. Cart 1 has a mass of m, and cart 2 has a mass of 3m. Cart 1 is initially moving toward cart 2 with a velocity of positive 2 meters per second, and cart 2 is initially at rest. Cart 1 then collides head-on with cart 2. If the collision is elastic, what is the velocity of each cart immediately after the collision? To solve this, we should follow the conservation of momentum procedure as we did with the other example problems. The first step is to determine the type of collision, which is easy in this problem because we're told that it is a 1D elastic problem. Then we should draw a diagram and then apply the two equations for a 1D elastic collision. Let's start with the conservation of momentum equation on the left. The initial velocity for cart 2 is 0, mass 1 is m, and mass 2 is 3m, so the equation becomes this, and the m's can be divided out, and V1 initial is 2 meters per second, so the equation now becomes this. We're left with the two unknown final velocities, and that's as far as we can go with this equation. So let's look at the other equation on the right. V2 initial is 0 again, and V1 initial is 2 meters per second, so the equation becomes this. And now we have a second equation with the same two unknowns as the first equation, so we need to combine these two equations. I'll do that by solving the second equation for V1 final and plugging that back into the first equation. The first equation then becomes this. And now we can solve for V2 final in this equation, and we find that V2 final is positive 1 meters per second. We can then substitute that result into the second equation on the right, and we find that V1 final is negative 1 meters per second. There are other worked out examples of 1D elastic collision problems that are posted as well. Now let's discuss the final category, inelastic collisions. As you know, linear momentum is conserved, so we have these equations as usual. And because it is an inelastic collision, by definition, kinetic energy is not conserved. So in an inelastic collision, we only have these two equations. In order to actually solve for something like a final velocity, additional information must be given in the problem. Often one of the final velocities is given. Here's an example of an inelastic collision problem. William Tell again shoots an arrow into an apple that is sitting on the top of a fence post, but this time the arrow goes right through the apple, still knocking it off the fence. The arrow has a mass of 30 grams and the apple has a mass of 90 grams. Just before impact, the arrow is traveling horizontally at 40 meters per second. Just after it passes through the apple, it is traveling horizontally at 5 meters per second. What is the speed of the apple when it flies off the fence post? We follow the usual procedure, first recognizing that this is an inelastic collision problem. Then we draw a diagram and write down the conservation of linear momentum equation. Because all of the motion is in the x direction, we just need the one equation, and we can recognize that v2 initial is 0 and substitute in all of the given values. And so we find that the speed of the apple just after the arrow passes through it is 12 meters per second. There are additional worked out examples of inelastic collisions that are posted as well. The final thing I would like to do is to provide a table that summarizes the recoil and collision problems that we have discussed in the last two videos. I'll let the table speak for itself, so that brings us to the end of this video, as well as the topic of linear momentum.